All right, welcome everybody to lecture number 10. We're now in week 4. I guess we're now in week 4, so we're well underway. This week we're going to finish up with chapter number 6. I'm going to catch you up on where the timeline is. Firstly, just before this lecture, I went and I added in some of these entries for the timeline. So you see that last week 7, 8, 9. We covered almost a bifurcation per day. And truth be told, I wish I went a little bit faster, but we went at the speed that we went at. So we looked at the saddle node bifurcation, lecture 7, transcritical bifurcation, and then the pitchfork bifurcation. So 7, 8, 9 takes you to the end of chapter 5. And then now we're going to start this lecture 10 with the local bifurcations part 2, and this is the chapter 6. In the notes, you'll find we haven't had a need for a new chapter yet. This is still chapter 6. And the problem set solutions for problem set 2 are also completely up now. So you'll notice that on Friday, I only put up number 1s and number 2, but number 3 and number 4 solutions are now there. And just a reminder, this week's problem set is problem set 3. And problem set number 3 is just going to take us to the end of bifurcation analysis. And it's kind of do both these kind of cobweb analyses and then a more detailed bifurcation analysis using these series approximations that we've been developing over the last week and a bit. So today we're going to look at chapter 6, this case B, the period doubling bifurcation. Okay, so to set the scene, you've assumed that your fixed point is, your bifurcation point is located at 0, 0. And if you remember, this is the main equation. We took the big F on the right-hand side and we expanded it out into a series. And this was the main equation that formed the subject of the last week and a half. Except previously, you assumed that the gradient of the function, this fx at 0, 0, you assumed this was 1. So this became a plus 1, and then the x's canceled on both sides, and we had to solve these equations of 0 is equal to a1 mu plus all the other higher order stuff. I think you do need a little bit of chapter 6 for problem set 3. So we had a discussion about this a few minutes before the class, but I don't think you need very much, and you can probably get whatever you need from chapter 6 just by reading a little bit ahead, or just by following the lectures and doing your problem sets on Wednesday afterwards. Okay, so this case B concerns this case where the gradient is equal to -1, and so now our interest essentially is to study this equation. So we want to approximate the solutions of this problem in which we're going to move the x over to either side. So we have 2x is equal to a1 mu plus b naught x squared plus so forth. And let me call this 1 here, let's call this 2 here, and let's call this 3 here. Okay, so again, the most straightforward balance, well, let me write down the most straightforward balance to try. So you'd try a 1, 2 balance, and you'd assume this is larger than 3, 4, and so forth. And again, the logic is as follows, right? 3, because x is small, is always much smaller than 1, right? 3 is much smaller than 1 because it's a higher power. Moreover, here, these terms that we didn't write down, you have terms like, for instance, like x times mu. But if you include the mu here, then x times mu is smaller than mu. And then this would be a mu squared, and the mu squared will have to be smaller than the mu as well. Right? So this is the most obvious balance to try. This is equivalent to the saddle node bifurcation. And if you balance 1 and 2, then this tells you that x is like a1 times mu over 2. Okay? And then you can verify that if x is like this, if x is like a1 times mu over 2, then indeed 3, 4, 5, 6, 7, etc., is much smaller than these two quantities. So this is a consistent balance. Okay. Now the other thing to notice from this guy is that this guy exists on both sides of mu, right? So this exists on both sides of mu. What about stability of this function? So we're going to take these fixed point. I was going to say these two fixed point, this one fixed point, and then we're going to check what the derivative of the function is equal to at that point. Okay, so fixed point exists on both sides, and let's check the stability. And to check the stability, we have to check the value of fx at this point here. Okay, this on the right-hand side is fx, so you take the derivative with respect to x. So take the local derivative, so fx is -1 plus -1, because we said it was going to start off at -1, and then you have a 2x times a b0 plus a b1 times mu, and then the next term will be a order x squared. Okay? Then you substitute this approximation into that function there. So notice that indeed at this location, the fixed point has a gradient of -1 plus something small. And you want to figure out, is this something small, is that going to be greater than 1? Sorry, is it going to be take you to be less than -1, or are you going to take you to be greater than -1? So thus, fx at this location here, a1 times mu over 2. You substitute in for this value of x, and then you simplify everything, and it gives you a -1 plus a mu. Okay, so you have a 2b0 times a1 over 2. So it's going to be a b0 times a1. And then the next one will be just a b1 here. Okay, plus ... Okay, so now this quantity here, it just depends on what this sign is, and this will just depend on different functions. The different functions have different values of these b0s and a1s and b1s. So regardless of the value of the function, when mu goes through 0, this will either go from unstable to stable or stable to unstable. Right? So regardless of the value of b1a1 plus b1, so the stability changes. At mu is equal to 0. Right? So just as an example, suppose that this quantity here were positive. Well, then when mu is on the left, when mu is less than 0, this will be unstable. If this is greater than 0, then it's unstable for mu less than 0, but then it's stable for mu greater than 0. Okay? And then if this thing here were negative, then it'd just be the opposite. Okay, so what have you concluded? Well, you've concluded that the picture has to look like this. if this is mu here, this is x here, you know the fixed point has to be a line through the origin, and it's going to be a line of gradient a1 over 2, whatever that number is. So suppose that number is positive, so you have a line of positive gradient. You also know that the stability has to change depending on what this value is. So the point is that on the left here, you have stable to unstable or vice versa. The picture might not. So the picture might have a line of a different gradient. It might be a negative gradient, and it might also go from dash to solid or vice versa. Okay. However, the point is that, as in this picture here, when mu goes from the negatives, you've got a fixed point that you're attached to, and you're stable. So the system, if mu is less than 0, the system will approach this fixed point here. But if mu is then incremented into the positives, then the system is unstable. And the question is, well, where does it go to? That's the conundrum, right? So here, the system is unstable off of that fixed point, but there's no other fixed points in the system nearby. Okay, I'll write that down. So, conclusion. On one side of mu is equal to 0, the system is stable. And it's it's going to approach that fixed point of, I don't remember what it was, it was a1 over 2 times mu. But on the other side, it's unstable. But there's no other fixed point. And so the question is, well, where does the system have to go? And so this suggests that the creation of a 2-cycle. Right? So you know that the system has to either approach a fixed point or it has to approach a cycle under the assumption that there is such an approach. You know it's unstable on the right here, and so this hints that there is perhaps a 2-cycle, and that's the thing that we want to find. Okay, so how do you get a 2-cycle? Well, to get a 2-cycle, you have to solve the equation x equal to f of x. So in theory, this is f of x here. You have to take f of x and then series expand that whole thing, and that turns out to be one big mess. But you don't have to worry about that mess. You don't have to know how to compute that. So we're going to give it to you. Okay, so how do I find the 2-cycle? You want to solve or approximate x equal to f of x. F of x, sorry. Okay. Now, since f of x is assumed to be near 0, then you can series expand the inner, and then you series expand the outer. So, i.e., you can have x equal to minus, essentially you put f of x into everywhere you see an x here. So it's a minus f of x here, plus an a1 times mu, plus b naught, and then this is an f of x squared, plus a b1 f of x times mu, plus would be 2 times mu squared plus dot dot dot. And you can see that it's going to be a big giant mess, because then you have to take this f of x and then resubstitute this line into here. Resubstitute this line into there, resubstitute that line into there, and so forth. Then you start expanding everything. And so you expand it piece by piece, and then you group all the terms together in increasing powers of x and mu. Oh, sorry, have I? So someone mentioned that I might have written stable for mu greater than 0. So however I drew my graph, I think this is the way I drew the graph with the dotted lines on the right and the solid line on the left. So the way I've drawn it should be stable on the left and unstable on the right. And then I think when I wrote down the next line, I might have used as an example something that was the other way around. So just make sure that if you write the notes for yourself, that you just make sure the diagram is as I've written. Okay, so, but this ends up being one giant mess, so you're not going to have to do any of that. Let's just say after some algebra, you're going to have x is, and then this we have to give you. In fact, I'm going to do this at the very top of the page here, just so we get a lot more room, if you don't mind. So you substitute this line into here, expand everything, group everything in powers of x, and group everything in powers of mu, and then expand it all out. And this is what you have. Okay, minus 2 times b1 plus a1 b naught x times mu plus a1 times a1 b naught plus b1 times mu squared minus a 2 b naught plus c naught times x cubed plus dot dot dot, once the dust settles. So remember a week ago, some people were asking, well, why use the method of dominant balance? You use it because trying to actually figure out which terms are in balance can be difficult. It might not be clear. So here what you're going to do is you've got 3 terms, and you're just going to consider all the possibilities. 3, choose 2 possibilities. And then find out which ones are consistent, which ones are inconsistent, and that should give you an approximation of the solution of that equation. Okay, so let's try all the different balances. So without any intuition, just try 1 and 2 together, I guess, just because they're close. They're the most immediate ones, and then take that to be much larger than 3 and 4 and so forth and so on. Okay, so if you try 1 and 2 together, you solve x times mu. So you're going to have on the left-hand side, you're going to have x times mu is like a mu squared, and then a1, and then a1 b naught plus b1. Remember that there's a sign change when you move it over to the other side, right? And this is over 2 times b1 plus a1 b naught. Okay, ignoring the trivial solution. That gives you x is like mu. Okay, except this also cancels here, this cancels here, and this cancels here, and then you're left with a1 over 2 times mu. And you would have noticed that this is just the solution that we found before, which is going to be a solution of this equation, x equal to f of x. So we've come to the realization that the most immediate balance, the 1 balancing 2, much larger than 3, just returns us to the normal fixed point. That's not the one that we want. So the 2 cycle has to come, and sorry, I've not checked the consistency. Let's just check the consistency. So 3 here is x cubed. 3 is an x cubed. And under this assumption, x is like mu, so this is like order mu cubed. And you can verify that if you have something that's mu cubed, then that's going to be much smaller than 1 and much smaller than 2. 2 is a mu squared, and mu cubed is smaller than mu squared. So this is a consistent balance. Okay? But it gives you the boring thing. It gives you the fixed point that you already knew about. So you're going to go and try a different balance. So let's go try 1 and 3 together. I'm kind of following the ordering that I tried the balances in my notes, but we can try, if we have a bit of time, try the other one and make sure that it's not. So we can try the 2 and 3 balance and then make sure that you lead to an inconsistency. Okay? So let's now try the 1 and 3 balance. So let's try 1 and 3 together, and that's much larger than 2, 4, and etc. So if 1 balance is 3, ignoring the trivial root again, because I have an x squared, I have an x cubed, sorry. So then I'll have an x squared is balancing. I've moved this over to the left-hand side, and on the right-hand side, I have a minus 2 b1 plus a1 b0. I've canceled the x from both sides. So this is now an x squared instead of an x cubed. Over, and then you divide it by this thing here, the positive version of it, b0 times b0. There you are. Okay, so as long as this thing, and then 2's cancel, as long as this thing here is positive, or sorry, if it's negative, then this quantity here will be positive, and you can take the square root. If it's not, then you just have to make sure that mu is appropriately signed. That probably didn't make any sense. I'll just write the next line, and you'll understand. So this is a plus or minus square root of b1 plus a1 times b0 over b0 plus c0. I'm missing a negative 1 here. I'll just do a minus mu like this. Okay. So again, as long as this, so these will just be numbers. Again, I keep on saying that, but I just wanted to click that, you know, for a given function, you will be able to calculate these numbers. They'll just be numbers. If these numbers together in the fraction are positive, then mu would have to be negative for the square root to exist. But if it's negative, if the fraction is negative, then mu will exist on the positive side. But the point is that this will exist on one side of mu. Okay? And okay. I'm going to call this a plus or minus just for my notation here. And this is our P2 orbit here. So this is our P2 orbit, or period 2 orbit. Or our 2 cycle. i.e., so x plus will be equal to f of x minus, and then similarly x minus will be equal to f of x plus. Okay, so it's bouncing back and forth between those 2 points. X plus sends to x minus, and then x minus sends back to x plus. It exists on one side of mu, and let's draw the bifurcation diagram next. fact, I'll draw it down here. So the bifurcation diagram is as follows. I think I drew it solid before and then dashed afterwards like this. This is mu here. This is x here. And so this was the previous fixed point. And you also know that it looks like a root mu. So you know that the arm comes out like this. Yeah, so this is x plus and x minus. I actually don't, yeah, that's right. It should be one should be positive, the other should be negative. And if you like, you can call this a P2, this little box here. There's your P2 orbit. No, why would the graph be wrong? Good question. No, so sorry, this, why do you think the graph is wrong? No, sorry, so I think what happened was that in the last graph, I drew it to be solid and then dashed. And then at some point in the example I gave, I said that it's stable on mu greater than 0. I think that's what one of the other people in the class said. But the graph is, so you could have drawn the dash on the left or draw the dash on the right. It doesn't, it just depends on the signs of all these various quantities. So the important thing is that you draw the arms of the P2 orbit, this orbit here, you have to draw them on the side where the system goes unstable. The point is that you're following the fixed point up to mu is equal to 0, and then when mu is greater than 0, you fall off. You're now unstable off of this branch here, and you end up landing on the two orbits and then going back and forth between the two of them. No problem. Thanks for the question. Okay, so this, by the way, is called a supercritical P2 orbit. So this is our example. Of a supercritical. P2 orbit. Okay. And again, I don't have a great way of remembering which one's supercritical. So I say super if it has two stable arms. And I say subcritical if it has two unstable arms for the pitchfork. Okay, but you can also have the case of a subcritical orbit. Let me erase this line here. But we also have the case of a subcritical P2 orbit. And in the subcritical case, just remember that it looks like a pitchfork, but with the two dashed lines surrounding a solid line. So in that case, you might have a picture that looks like this. And I think we'll give you examples of each of these in a second. So which picture you have just depends on all the various all the various constants in these functions and how they interact to give you those formulae that we wrote down before. The example I'm about to give is a supercritical pitchfork, but I wrote in my notes that in the typeset notes there is an example of a subcritical pitchfork. And someone asked, is this example 6.2? Maybe let's have a look together at where we are in the notes. No, you can think of a pitchfork. So if you define, it's a good question. So the question is there a difference between a P2 orbit and a pitchfork? You can think of the P2 orbit as a pitchfork of the doubled map, the f of x map. So if you think of G as f of x, then you can think of the pitchfork that we found previously in case A is a pitchfork of the G map, of the f squared map. Okay, so we've done the balance. So we start off with this equation here. We did the local balance of this equation. We found this solution here, which was the standard fixed point. And we showed that this standard fixed point is stable on one side, unstable on the other. And we said, that this has to be an example. There might be some more going on because it goes from stable to unstable. And so you ask, well, what happens on the other side? Okay, so then you look at the doubled map. This is the x is equal to f of x map. And then you do the series expansion, and then you simplify everything and group things together. And eventually that leads you to this equation here. Okay? Then we called each one 1, 2, 3, and then we did the local balances of those three terms. Now in the very first possibility, we ended up with x being a1 times mu over 2, over here with this equality here, and that returned us to the standard fixed point that we know is a solution of the doubled map. On the other hand, if you go with the 1-3 balance, then you're left with this equation for the two arms of the pitchfork, of the P2 orbit. Okay? Just a final remark. I won't write it down on the board. Regarding the codimension of the period doubling bifurcation, we did not need to specify any additional constraints on the coefficients AJ, BJ, etc. above. And furthermore, we suppose implicitly the important coefficients did not vanish, for example, C0. So it follows from the period doubling bifurcation is just as typical in maps as the saddle node bifurcation, i.e. the period doubling bifurcation has a codimension of 1. So you remember the codimension is sort of the number of constraints you need to guarantee that this bifurcation comes up. Modulo any, you don't count any degeneracy condition. So here, notice that this solution for the arms of the pitchfork, arms of the P2 orbit / pitchfork, requires that B0 plus C0 is equal to 0. Because if this was equal to 0, then this approximation breaks down. But you don't have these degeneracy conditions in your codimension count. In your codimension count, the only restriction on the function is that this leading term here, you see this minus x, this leading gradient is minus 1. So it has codimension 1, just like for the case of the saddle node bifurcation. Okay, and then in the notes, it goes through example 6.1, which is a supercritical pitchfork bifurcation, and then a subcritical pitchfork bifurcation. So someone was right on the mark when they said that this subcritical example is example 6.2. By the way, just because I promised to do so, and I'd be lying, I promise a lot of things that I often don't do, but I did promise this. I promise you that we were going to look into all the balances of that equation of three things, and I'll just do it very roughly here, just to convince you that the 1-3 balance was the right one. And if suppose that you didn't know how to do this and you went and said, I'm going to try the 2-3 balance instead, would you have gotten an inconsistency? That's the question. You know, this is hold on, let me just finish writing this. All right, we call this guy 1 here, we call this guy 2 here, and we call this one 3 here. And we first did the 1, 2, and we said that was boring, that led us to the usual fixed point. Then we did the 1, 3, and then now, what if you went and did a 2-3 balance? Would you have been led to the right conclusion? Well, if you do a 2-3 balance, you balance 2 and 3, and let's say you say that's much larger than 1, just try it, right? So if I balance 2 and 3 together, that's going to give me on one side, it's going to be dot, dot, dot. I have an x cubed. On the other side, it's going to be dot, dot, dot times a mu squared. So then you solve this guy here, and it gives you dot, dot, dot mu to the 2/3. Right? So then you say, well, is this guy truly bigger than 1? But 1 here is order x times mu. So if this is mu to the 2/3, this is order mu, and then I have to add 1, that's 5/3. Right? 2/3 plus 3/3, that's 5/3. So 1 is mu to the 5/3. Oops. All right, but 2 is mu squared. Sorry, it's order mu squared, which is order mu 6/3. Right? Which is much smaller than 1. And that's an inconsistency. So you assume that 2 and 3 were much larger than 1. Assuming 2 balanced 3, you solve for the x and you found it was mu to the 2/3. Remember, mu is always small. If x is like mu to the 2/3, then necessarily 1 is then mu to the 5/3. But if 1 is mu to the 5/3, you can check that 2 and 3 are mu to the 6/3. And you know that mu to the 6/3 is much smaller than mu to the 5/3, when mu is small. Right? Bigger powers are always smaller. So this is an inconsistency. Yeah? So maybe it's uncomfortable because I always seem to do the right balances. I never go through the logic of the wrong balances. But the point is that if you did the wrong balance, you should have come up with an inconsistency. Now, if you didn't come up with an inconsistency, then perhaps it's telling you that there might be another solution to the problem. Now, by the way, for this problem, it's not obvious to me how you know that there couldn't have been another solution to the problem. Good question. Okay. You know what? I've got 5 minutes. I've been really bad this year, and I've never ended on time. So I'm going to end it now. We're going to go through that last example of the supercritical P2 orbit. You've got the example of the subcritical P2 orbit in your lecture notes, and that will take us to the end of chapter 6. But then it's good for us to start off this next class just reviewing this theory, and that means we get to do this example on the Wednesday class. Okay? Otherwise, enjoy your last 5 minutes. Thanks, everyone.